Question 3, really big question, 20 marks worth, testing lots and lots of different parts of the syllabus. So the first part of the question, explain why this is a disproportionation reaction using oxidation numbers. So just remind ourselves, what's disproportionation? It's when the same atom is oxidized and reduced. So if we look at the phosphorus, it has an oxidation number of 0 because it's an element. So if we move over to this phosphorus here, it's bonded to 3 hydrogens. Each of those hydrogens has an oxidation number of +1. We know that from our rules. So the P must be -3. That's a drop in oxidation number. So there's your reduction process. If we move to the other product, this NaH2PO2, we've got a 3 in front of that. That doesn't make any difference to the oxidation numbers because effectively it's doing the same thing to everything in the equation, or in the formula, sorry. And so we can ignore those numbers. So remember the rules. Group 1 in a compound, +1. Hydrogen, +1 each. So we've got 2 of those. So we've got a +3 so far. And then if we move over to the oxygen, each oxygen is -2. So we've got 2 of those. So we've got -4 from those 2 oxygens. So we've got +3, -4, but the whole thing's neutral. So the P must be +1. And that is an increase in oxidation number. So there is your oxidation process. So it is disproportionation because the phosphorus has been oxidized and reduced. Calculation starts now. We've got a mass of P4. And we need to find the volume of phosphine gas in centimetres cubed, not decimeters cubed, produced at RTP. So if I just go back up to the equation, so we're going to calculate the moles of P4 because we know its mass and its MR. So you can see there, moles of P4 is 0.015. The mole ratio to pH3 is 1:1. So we're going to get the same number of moles of pH3. And then we turn that into a volume because that's a gas. We multiply the moles by 24,000 and we get 360. The equation, well, they give you everything you need for the equation. So your starting point here would be an unbalanced equation. pH3 phosphine plus the O2 from the air is making this oxide of phosphorus P4O10, which was given, and water, so H2O. Then I'm sure you can balance that yourselves. And we've now got the calculation starting for proper, and we're given some information to justify why Na3PO4 is a salt. So quick reminder, what's a salt? It is when the H+ ion of an acid is replaced by a metal ion or an ammonium ion. So why is Na3PO4 described as a salt of this acid? Well, the H+ ion of H3PO4 has been replaced by a sodium ion, or 3 sodium ions. Calculate the amount in moles of the acid in 15 centimeters cubed of that concentration of acid. So we need to use our moles concentration volume formula triangle. Moles is concentration times volume. And remember, volume must be in cubic decimeters, so we divide the centimeters cubed by 1,000 and put that into the formula, and so the moles comes out at 0.0015. And then that's going to feed into this part of the calculation. The equation for the preparation of Na3PO4 from sodium hydroxide and phosphoric acid is shown below. Calculate the volume of sodium hydroxide of this concentration. That would react exactly with 15 cm cubed of 0.1 moles per decimeter cubed H3PO4. In other words, that many moles. So the moles of acid we've already calculated. The mole ratio is 3:1, so there's 3 times as many moles of sodium hydroxide. So we multiply that by 3, we get 0.0045. So we need to turn that in, we need to find out what volume that would require. And so volume is moles over concentration. The moles is 0.0045. the concentration 0.2, and that comes out with 0.0225 decimeters cubed. They want it in centimeters cubed, so we multiply by 1,000. The question takes a bit of a change in direction now. It's going into bonding and intermolecular forces and the like. So we're given some information about NH3 and pH3. We're told they're both simple molecules, and there's the boiling point in the table. So the main intermolecular forces between these molecules, well, NH3, we've got a nitrogen bonded to a hydrogen. That's one of the top 3 electronegativity atoms. Remember, it's phosphorus, oxygen, nitrogen in that order. And so we're going to get hydrogen bonding between NH3 molecules. pH3 molecules are polar, but it wouldn't be hydrogen bonds. So there would be permanent dipole-dipole intermolecular forces between pH3 molecules. Suggests why pH3 has a lower boiling point than NH3. Well, if you know the order of strength, hydrogen bonds are the strongest intermolecular force. Permanent dipole are a little bit weaker. And so more energy is going to be required to overcome the hydrogen bonds compared to the permanent dipole forces. Another definition. What is a dative covalent bond? It's a shared pair of electrons, that's the covalent bit, where both electrons have been donated or provided by the same atom. So remember, nitrogen has a lone pair. Boron's in group 3, so it's only got 3 outer electrons. So we're going to have to draw this up as a dot and cross diagram in a minute, but there's your dative covalent bond there. So you can see I've drawn the dot and cross. If you imagine this without them joined together, you'd have the ammonia, there's the lone pair, the BF3, so that's electron deficient, so you can form a covalent bond between the nitrogen and the boron by this pair of electrons from the nitrogen. Bit about bond angles now. So in BF3, so if you can imagine this without that lone pair, it's a bit difficult, sorry. There are 3 bonding pairs of electrons in the valence shell of BF3, all repelling equally, and so the maximum sort of distance apart is 120 degrees. The bond angle, the FBF bond angle, so that's there to there to there, in this molecule here would be 109.5 degrees now, because we've got 4 pairs of electrons. These are all bonding pairs, so the repulsion is equal, and so we get that maximum distance apart at 109.5 degrees. And then the final part of the question, the H and H bond angle in ammonia is 107. Student predicted that the H and H bond angle in H3NBF is larger. Explain why. So if we go to the diagram, again, if you can try and imagine this without this BF3 on, we've got 3 bonding pairs of electrons and 1 lone pair of electrons in the valence shell. So we've got 4 pairs of electrons. They all repel each other, but the lone pair repels a little bit more. And so the starting angle for 4 pairs is 109.5. That's reduced by the extra repulsion from the lone pair by about 2.5 degrees. And so it drops to 107. Whereas in this molecule here, the H and H bond angle is 109.5 degrees, which is larger because we've got 4 bonding pairs now. That lone pair has now become a bonding pair, and so the repulsion's equal.